Here we go. Hey, welcome to Coffee Compiler Club. Here today, normally talk about compilers and language runtimes and I don't know, all kinds of other things. And also talking like random startup stuff with database, block storage startups. So who knows where the conversation goes. Everyone's being recorded. You show up on YouTube in a couple hours. That's it. If you wanted to say something, Chris, on the recording, but don't know. Yeah, no worries. So we have people here. Let's see. James, have you introduced yourself in the last club or not?
I did. Yep.
Okay. And then Kenjin, you're new here, right?
Yeah, I am.
You want to say like 10 seconds here?
Yeah, sure. So I'm a C Python core dev. I work on the JIT compiler, which isn't ready for production yet. But yeah.
For Python?
Yeah, for Python.
For C Python or PyPy
Yeah.
or which
Yeah,
of 10?
not PyPy, for C Python.
For C Python. Okay. Which I thought they had known they had well, maybe that is exactly it. They have a lame initial jet.
Yeah, that's the story. The JIT can't
Okay.
JIT generators very well right now.
And are you working on, I mean, is the GIL, the global lock, like gone or missing, or you
Yeah, I used to work on that, but then I left my previous job. So my previous job was working on that, but I'm still working on it. Yeah, and there's quite a bit of cool stuff we are doing in there. Like the stuff I implemented was type pointers and deferred reference counting in C Python. So yeah.
so something's going on, but there's still a
Yeah.
GIL in the current generation of Python
In 3.13 is gone in an experimental version.
in experimental. Okay. Yeah, all
Yeah.
right. Interesting. Well, okay, fine. So anyone want to open up a topic, or I'll poke Arthur about aliasing in simple and sea of nodes, because you and I went round and round on what it means to alias or how you call aliasing after I let Levo in here. Levo, why are you being there you are. Fine. So this is the I'm throwing out a topic to get things rolling. This is the equivalence class aliasing stuff. And the terms used by LLVM are different, and I'm not certain that there's a one-to-one mapping between them. So the intuition for equivalence class aliasing is you break up the space of all of memory into equivalence classes. These are just, you partition memory into unrelated chunks. And each chunk gets an alias number. And if you're in the same chunk, you alias. And if you're in different chunks, you do not. So it's always a yes, no. And then because it's in this yes, no format, you can directly represent it in the graph using nodes and edges without having a separate alias infrastructure. There is no separate alias infrastructure. It's just nodes and edges that tie together loads and stores in the same class and run parallel and unrelated along unrelated classes.
So why do you need aliasing?
It's precision for its performance. So there's the obvious optimization is I have anything that's got a struct with some fields and I'm strongly typed, then I can say all those fields of that struct are not related to each other. And they're not related to other structs of different classes. And because they're not related, when you refer to elements of those fields, they don't alias. They get their direct memory edges point to updates and reads and writes to individual fields, but not to other unrelated fields. And then the optimizations around them all turn into simple peoples because you don't have to ask the aliasing question. The aliasing question has been answered directly in the graph.
So the way I understood it, when you have two memory accesses that belong to the same equivalence class, it doesn't mean that you can, so let's say you have two loads from two different memory locations, but belonging to the same class.
Alias class, yeah.
Yeah, you cannot replace one load with the result of another just based on this information?
So it's the two loads are themselves not candidates for CSE if they have different memory inputs or different pointer inputs. Right. So the
you
classic
can
CSE, it's same opcode on same inputs, just hash table
But-
lookup.
But you
So-
cannot use the memory inputs for CSE. You need to rely on the equivalence of the pointer operand as well.
Yeah. Yeah, it's both.
Okay, so
the
Mhm.
memory input and the pointer have to be equivalent. It's a standard CSE. Removing redundant loads to the same field turns into a standard CSE. I'm trying to pull up the graphic. Which is buried in here, but keep going. I'll have a graphic up in a minute, but I don't have it yet.
So yeah, I think that's the difference in terminology, is that this case LLVM calls may alias because it may or may not actually point to the same memory. You're just not able to disambiguate it at compile time. And an example is you have two pointer arguments. You don't know which values are passed, so you have to put them into the same class. It is always correct to say that they may alias, but in your terminology, you put them into the same class. But there is a stronger property that LLVM's alias analysis can give you if you ask about some memory accesses, which is must alias. And in this case, you can do like what you call CSE just based on this property.
Okay,
And
so
it doesn't have to be the same pointer values, but somehow through alias analysis, you can prove that it actually points to the same memory. For example, because there was a dominating equivalence check, and that's how it figured out.
right, in sea of nodes, if I do an equivalence test, then I will use that to make them have the same definition point, the same edge, and then it'll go back to the standard CSE of same input, same opcode.
And for,
Well, yeah.
for terminology, I think that terminology is from program analysis, because you may have may analysis and must analysis. So the LVM alias analysis is just a special case of that.
So,
Yeah.
okay. I'm not doing any special alias analysis because I'm relying on the strong typing I get from the language.
Well, but you do. It's just in terms of in LLVM terminology, you have one specific mechanism of doing this analysis. You use typing information from the language, and
Yeah.
in LLVM there are various alias analysis. Some of them are type-based, others are like what is called basic alias analysis, just looking at the expressions and trying to answer these kind of questions. And we, for example, have a downstream alias analysis that does exactly the same what C2 does for Java using type information.
Yeah, I'm not
and-
claiming that the analysis I'm doing, the equivalence class, I want to say is almost surely weaker than anything that LLVM does. It only collects a subset of things that are known aliasable or not aliasing or anything. The difference here is that the cost comes essentially for free. So as a compile speed thing, it's this giant benefit. And actually implementation wise, there's no work on the implementation and no work on for speed purposes to get that information into the graph and then optimize based on that information, so that the end result is I get for very low cost, both engineering and runtime or compile time, I get in the distant past, papers came out and said about 95% of the performance gains you can get out of the most powerful Oracle-based aliasing, a perfect alias analysis. I will get very close to what a perfect one would get.
So LLVM has something which is conceptually similar, just implemented in a different way. That's memory SSA. Unlike your graph, memory SSA is a side structure, it's kind of side analysis that can be built on top of IR. and can give you the same kind of equivalence view. And for memory accesses, you can see the dominating, the previous memory access that defines the current state of memory. But this thing is optional and can be built on demand, can be updated if you want to preserve it. But also you can have a transformation that doesn't know how to update, doesn't care, and you can drop it and recompute it later. So I think it's a trade-off that if you have it as a part of the graph, as a mandatory part of the graph, then every transformation needs to know how to update it.
So just be careful here. It is part of the graph. Every transformation needs to update it. 99% of the transformations do nothing and are correct without being aware of it. When you say everyone has to be aware, it has to update, the real answer is loads and stores have to care. No one else does.
Okay, well, yeah, every time you are modifying memory accessing instruction.
Yeah, every memory accessing instruction cares about memory, yes.
Mm-hmm.
And they do an obvious local people transformations. So what I have in this set of slides here is the obvious local people transformations. One of the things going on here is that every node has obvious local people transformations. So there's built into the infrastructure for manipulating obvious local peoples. The memory guys just do the same thing on the memory edge. They can't tell, they don't know. As far as they're concerned, they're doing a local memory. Local people happens to be on the memory edge. Like I said, they don't care. So it's no effort to write those peoples. They behave exactly as you would expect. If you write them, like I've shown in the past, it's typically a couple lines for the people validation, and then 1 or 2 lines for the transformation. It's very short.
Yeah. I like how some of the things, how unification of different dependencies in the same way on the graph makes some of the transformations really straightforward. Like what you described with CSE, you just check that all inputs are the same. And you don't differentiate like, okay, I'm reading from the same pointer, but I also need to make sure that the memory location is unmodified. Because you unify this as just, well, there is an dependence edge and you need to make sure that all dependencies are the same. So that's a nice property. I think, yeah, it simplifies it.
Okay. I've shown this slide before and the following slides. Does anyone care to? We have some new people. I don't know if you guys care. Otherwise, I'll do the 5-second and be done here. The only thing I'm showing here is the whole graph. No, here is just the memory edges. There's a fees for memory. There's loads. The red is memory. Loads using it. There's a 1 store. It's both using and defining it. And then I break up the memory into equivalence classes. 1 for the iterator field, 1 for the array length, 1 for the array body. And that breaks up into a bunch of new memory edges, but most of them are just unrelated, parallel side-by-side graphs, and then you optimize on that. All right, Chris, nice seeing you. And then after you do all the usual peoples, they just clean up and you get this sort of very obvious, hey, all these loads and stores are independent. So that's it.
I think what is interesting that this memory aspect is not it is not a mandatory part of C of nodes representation. You can have a C of node graph where you don't have an explicit memory dependence. You just have a control dependence between stuff that is dependent on memory.
You need some kind of edge between unrelated loads and stores so they don't bypass. Yeah.
And you can separate the alias analysis and memory SSA into a separate structure the same way LLVM does. So, and then I think in theory you can also look for other kind of dependencies. I don't know if there are useful ones that you can explicitly express in the graph.
Right. So here's where this gets tricky, because I tried this in C2 several times, and the sort of the story comes around. If it wasn't preserved, the knowledge you gain by local analysis and you make some sort of local transformation, if that wasn't sort of directly preserved in the graph, some later person would come along and not understand what you did or how you did it, and would then make a further transformation that was just broken. And so I could get away with it in certain kinds of very local situations. So these would be, take an array that's doing a Saxby-Daxby thing, and you unroll it, and you get a bunch of parallel loads and stores. And then you can prove that because it's +1, +2, +3, +4 for the different loop iterations, they are all guaranteed not aliasing. And you could break that up in the graph, and that would work. But there are a bunch of places where I attempted to do things where I said, if x equal y, then x and y are the same, and so I'm just going to use y's for x's, and that was okay if I did it directly as I parsed the graph. And so I immediately said, whenever I see a textual x, put a textual y, and life goes on. But if I discovered it later as you inline and optimized and cleaned up things, I couldn't go into the if true side and find things that looked like they were the same value as the values you were looking for x and y, and replace one with another, without it having far-reaching consequences that were broken. So it was very difficult to. I did it a few times, and it was never worth it. Like in terms of the complexity of engineering, to grab something that was outside of the equivalence class. So kind of a. I mean, you could argue that I didn't do it right, or there's another answer, but the obvious, it's in the graph. I can prove something usefully locally. I make a transformation, but that was sort of not equivalence class based. Somebody else, somewhere else, almost always found me out, but wasn't asking the same question that I had just asked here locally, and would then make a further transformation that was busted. It was very.
So you're saying if you don't express the fact that you used for transformation in the graph explicitly.
Yeah, if it wasn't explicitly
then,
graph, if you got it all contained within the graph, you were good. But if you somehow were able to say, since x and y are equal here after whatever thing's going on, and somewhere inside of here I have a thing which it's not called x anymore. It's like x and y were from the parser. But after the transformations run a while, x and y are from like a long series of optimized code. They were inline things and this and that. You have an if test that says these two unrelated nodes. Okay, somewhere in the body of the then clause, you say, oh, here's two loads. They both point to one to x and one to y. I'll claim they're CSEable. That immediately conflates the equivalence classes for x and y globally, not just locally. And then you're busted.
Is it possible to first update the memory part of the graph? Although I don't know if you can express this locally for a specific context.
Right, exactly. So there was a theory that I ran through that I never implemented that said to do that kind of a thing, I would also need to put in a memory merge node that said these two alias classes are temporarily the same, or these two memory states or something. There was something that said these are temporarily the same, and then as soon as you left scope, where you're out of the if test, they broke apart again. But you couldn't let somebody see from the loads that one of the loads or the other of the loads picked up a memory edge that you weren't sure where it came from. Suddenly he was saying, oh, now these things are in the same equivalence class. And that was where you would get breakage from. So you needed some way to say, as soon as I leave scope, you're back to where you were, and somebody who's pointing at the load and then peeks through the load's memory would instead peek through and say, oh, I don't know, this is a Union memory class. I never got that worked out.
Let's say in that example with a comparison, equivalence comparison, let's say you do a local transformation, just looking at the comparison without consulting with the memory dependence graph. You say that bad things will happen later down the line.
You need to consult here. Let me share the doc. We'll write this example and make sure we understand we're talking the same language here. So I have some pointer class, whatever, I don't care, you know, P, Q, standard C pointers, and they're equal to something, who knows? And then I've said here, oh, and here's a bunch of code. Who knows what the code does to P and Q? And then I said P equals Q. And then in the body here, I'm like, okay, I want to have X is, P dot X field. And Y is P dot Y field, P dot X, oh no, Q dot X field. And then I'm going to do something further with, with those guys, and then else, and life goes on. Okay, so here, since P and Q are the same, these values must be the same. And of course, this crack must be 0. And you could fold all that up. In order for them to be the same, you also, maybe this is something related to also the memory edges. So the load here has two things. It has a, this is a load op, it's got a mem, and it's got an address. So for them to be the same pointer, oh, they're using the same memory there. So the memory here is whatever the memory state came in for the alias class of P and Q. They have to be using the same alias class. Somewhere up here, in order for P and Q to be the same, it must be that mem of P and is equal to mem of Q, or else you already have an unrelated bug.
Okay, so the memory graph doesn't give you this optimization straight away because you do not have this equivalence of memory states for P and Q.
You're looking for a CSE. I would get this from a CSE. So first thing happens is there's essentially a cast that P equals Q, which really means replace Q with P in scope. And now they CSE, and then you fold up, you get a 0. I'm trying to remember the failing case. I had several instances I attempted and backed off from, and there's still one left in C2, which has a very complicated pile of crap. It was always a range check that led me down the funny path. Well, that was the one I kept. Maybe I'm just being faulty memory here. This
if you do
terrible.
If you replace P with Q, then yeah, everything is straightforward after that.
Yeah. No, I think here it's obvious. The other one where it was always okay was I did a profit check that said if I replace P with Q, then the result just folds up. And then as soon as the result folds up, there's no shenanigans about somebody who's also using Q far down the line being confused, discovering a P. That would be a case here where I have some unknown function that gets inline. And he's busy in the inline section. It's inline, uses Q, right? Except that Q got swapped out for P, except it was supposed to, and it didn't in the unknown function until it inlined.
If you mistaken P and Q, what's the easiest way for you to figure out where you went wrong?
Oh, you mean in terms of a compiler bug?
Yeah, like how would you debug that?
Yeah, okay. So this is a sort of in the realm of I'm just right on the spot. You do the obvious thing and you unwind and you go forward. So I have a known thing. All my tests pass. I add a new p-poll, tests break. I debug the test and I discover my p-poll is fucked. I unwind my p-poll. Test is good again. Okay. I'm assuming it's the p-poll and I stare at the p-poll. If instead it's the case where things were working, things broke, the people or the change I did was not related, and I've just uncovered a long ago, far away bug. Now I have to do a serious debugging hack and figure out what happens here.
Yeah.
Okay, well, so that's sort of the normal thing. In simple, well, C2A, all these debugging things, I'll usually start by turning on the hefty assert, which says that the graph is sane at every small p-poll step. And that's an n squared assert. And you usually break not at the people where you originally thought you were, but you break much earlier. Something stupid happened earlier. And then you start looking at the graph. The sort of worst case scenario, and it used to happen in C2 a fair amount, and then until I got the big assert thing sorted. The worst case scenario is that you do something stupid, you prove false is equal to true, all tests suddenly become, everyone becomes unreachable, the graph entirely goes dead, and the program, the compiler halts with the empty program. The program says, okay, I'm done, and the answer is return 0. And the whole program's gone, right? It's just optimized away. And that's because more or less compilers are big theorem provers, and if you prove false is true, who knows what the hell happens after that. So in those kind of scenarios, I had to start looking for when things started to go away, get deleted when I knew they were alive. And I have places in the, it's same as anyway, probably got places where your DCE is picking up, hey, I'm throwing away an obvious thing that's part of the final solution. Okay, why did that break there? Okay, and why did that die? Well, the prior thing died, and the prior, and the prior, and the prior, and you have to roll it backwards to find out where something happened. Again, usually I can tell not too soon where something in the program graph got busted, and then I set breakpoints when I edit in that area. You're starting to edit around where things go broken, and then pretty soon you get there's a counter in the peepholes because it's all deterministic, and you get a counter and you look and say, okay, on and around count number 1,000, graph went south on me. And you back it up a little bit and you start looking for what peepholes are happening that are editing right there. So there's, if you do this on a regular basis, there's strategies you use to go sort out who broke.
Okay, I can understand all of that, except for what specifically would a person need to do to make sure their graph is sane? Because it sounds like ad hoc stuff that, because the way I'm imagining is ad hoc.
Yeah. So
Oh,
it is because your program semantics. And if you write a program that tries to prove Fermat's last theorem and you screw it up and instead you get a prime counter, both programs are exciting and do something big and complicated, but one is not the other, right?
So it's not something generic that would work on like all input programs. It's
No, that's the halting problem. You can't do that.
Okay. I get this.
Okay, but what I can do is validate a local correctness. So I can say every node computes a type which is strictly equal to or better than their current stored type. So as part of the pessimistic lift all the types in the program uphill, every node has a current value, and there's a work list of things that are changing that have changed recently. You're going to inspect again. If you visit every node, it's always the case that if he looks at his current inputs and computes a new type, it's monotonically better than what he's got. So that one breaks pretty easily if you've screwed the graph up. So that's one of the breakages. Another one is you don't get to delete away like start or for being unused, start or stop or return, whatever. There's a couple things you can't say go dead. They never go dead. If they do, your graph got broken. The other things are typically, I just take an assertion check of whatever kind, and then I work it backwards from there. So you're saying what is locally correct? Oh yeah, loads and stores have memory inputs. They all locally check themselves that their memory input is computing a memory value, for instance. If you break those kind of ways. Those kind of breakages are typically not, that doesn't happen that often. You screw up a peephole that said, hey, I think I'm going to, oh yeah, well, there's one we did one in Simple that did fall down that path not that long ago. Simple has a clone through fees. I don't remember what chapter that showed up in. Probably available already here. Well, now, why are you not? There you go. There you go. There you go. Fee. See, oh, no coloring. Come on, GitHub. Surely there's coloring. No, there's no way to colorize. How the hell? Pull down a comment. Maybe I'll put it on the loads. This is, oh, this one hit too. Pull down a common op. One less op in the world. So the pattern described here is if I have a fee who's got an op, maybe more. There's a missing ... in the documentation here that just says a phi of a bunch of ops, then I can make an op of a bunch of phis. And I get one fewer op in the world and one more phi in the world, but phis don't make code. Okay. So this is a very generic thing. He's like, hey, I'm gonna limit myself to 2 because I'm lazy, and I'm not doing anything bizarre with control flow nodes, and same op, which we can look at what it does in a minute. Then go ahead and pick up a collection of inputs, set my regions up, copy the inputs left and right, so I make my phis, make a new phi on the left and make a new phi on the right, and make a copy of the op down below that uses a phi. So it looks pretty generic and doesn't matter what op is. Turns out it did matter what op is. And I occasionally did wrong things to op. So op said, the same op, it just says they have the same class in the lattice. So that's all fine. Somewhere in here, I was setting the type here. I was setting the type of the phi to be the declared type of the existing phi. This is the bug. So if I have op as an add and I have a phi of 2 adds, I'm going to get an add of 2 phis. And an add is an integer op producing an integer value, and the phi was declared. This phi is declared an integer type because won't highlight now, because he's 2 adds. Or he could be 2 float ops. This is all great. But it turns out if I have a load, this same transformation works on 2 loads. So this op is a load, and this op is a load, and A is a memory, and B is a pointer. And Q is a memory, and R is a pointer, and so on. But when I do this phi is a memory phi, but the load loaded something, say a float. So the type of this phi is not float, it's memory. And the type of this phi is not float, it's, get it highlighted? Yeah, this is a pointer.
So how do you look up that return type?
Well, I had been doing it by the current local variable called the declared type on the phi. That was incorrect. So chapter 10 has this known bug we've left in, and it got fixed later here in one of the later chapters, and I don't remember which chapter actually did the fix. And it might be that it's in my current workspace and not pushed in chapter 15, but we're going to find out. It's just a lot slower poking around here. Yeah, here it is. Here's the fix. I make a new phi, but the type of the phi is, well, it's a sample one of the inputs of A or Q, and I get his type, and then I get his greatest lower bound. That's equivalent to the declared type. The declared type is just greatest lower bound. So labels a debug field. That just gives me a hint for the name. It has no semantic meaning. Input 1 of the self phi gives me the left-hand op. I get the input 1 of the left-hand op. That gives me what we call A in the comments above here. And I get his type and greatest lower bound. So that gives me a memory edge for the left-hand phi and a pointer value for the right-hand phi. And then everything else here is the same. And then here is new. This said, go ahead and compute the phi ops type. And then there was another bug that came around, what we could argue, I could go back and forth on, where under rare conditions where I have integer overflow that only happens if I do it after the phi, the adds after the phi and not before the phi. Because of wrapping, I lose precision. And then I throw a type assert saying you didn't lose precision by doing one of these transformations. And I thought, you have to be doing overflow on purpose to hit here. So I'll just, I'll just cut out and don't do it. This is one of these things where I have a, max int, min int, or max int, and I'm adding small things to them and they're going to overflow, but they're not quite max and they're not quite. So when I add below, phi them, and then I add below, I overflow here or overflow there or whatever. There was a test case that Zamelia came up with, Nick maybe came up with that said, you can wrap overflow and lose precision. Okay, fine. So here's the current version of that same transformation, but the bug that bit me for a while was I was saying the declared type of the self phi, but it's not. It's the declared type, if you will, of the op left edge and the op right edge. Didn't matter for adds and add floats and any of the integer ops. Didn't matter for loads, or the left input was memory and the right input was pointer. So, and again, like Leo, you asked, how do you debug these? This threw an assert pretty quick. The old code would throw in a declared type, which is the loaded value, which would have been like, I say, int, in a feed that was supposed to carry the memory. Promptly, that feed would feed into some other loader store, and the first thing that loader store would do is say, grab this thing, it had better be a memory, and it's not. You throw a typecast, you die. Oop, graph's broken, what happened? And then you roll it backwards. And then generally, if you, and those kind of things, the def came really quick, so you look at the peephole counter, and you subtract a few, and you stop a little earlier, and you look at the graph, and then you run till you crash, and you look at the graph, and it's usually pretty obvious. Like you've narrowed down the set of things that are happening anyhow.
That sounds exactly how I debug my code generation.
Yeah, there's nothing, right. There's nothing super special here, other than knowing where to go go find things. So here's the useful debugging. There's your counter. Wow, work loop, bump counter, run peephole. Somewhere in here, I get a crash. I look at that counter. Then I set a breakpoint on the counter. Stop when the counter is equal to blah. And you know, you're pretty close to the problem right there. And here's the n squared assert here. That's turned on always in simple because our programs are small. And in fact, if it finds a bug, break here for bug, you set your breakpoint there. And then if you hit that, you exactly at the peephole that broke you, you're exactly finished the peephole that broke you. So that's very useful, sir. You can go back uphill and look at the node and see, who it was and who it became, and what peephole is usually pretty obvious which peephole exactly did it. So yeah. All right.
I'm not sure you would want it for simple, but I assume for a more mature language, you might want an unchecked int type that would be more a checked int type that would be more complicated because it was guaranteed it didn't roll over. No?
The monotonicity check goes a long ways for on the types. The other structural tests, I've had bigger asserts in that run and confirm more interesting things. But the monotonicity check, like I said, that one goes a long ways. One of the things here that goes hand in hand is I attempt not all, I attempt, and well, that's not true here, and not in simple. In AA, I definitely attempt all transformations. And if the transformation would fire and you're not on a work list, that's a bug. You should. The assert is saying you can fire this transformation. You should have been on the work list. Okay, great. Actually, simple has a bunch of those in a different place, so that's fine. But that attempt at a transformation also internally asserts all kinds of things. So you generally don't get too far before you trigger an assert after you've broken the graph. Like I said, in the land of C2, originally when I was first running this, I frequently had places where it went a long time after you broke, and it took a while to sort back as to where the breakage happened. I figured out how to test for that better now in both simple and AA. It's pretty quick between breakage and when an assert triggers. Sorry, I'm deleting things. Okay. What else?
So what is the status for a runnable implementation of AA?
Well, so I got busy with making money and doing contract work, and I kind of sorted and then I just had this like a month and a half where I had standard vacation to Crete, go to my mom's funeral, standard Burning Man. I ran out of time. So my current theory is this weekend I'll do some AA. I'm looking for a raise on simple and AA to make progress. And then I'm going to be picking 1 week out of 4 to do strictly AA things. So I have 2 pending contract works that take up 3 weeks out of a month, and I have simple on the halvesies and AA on the halvesies. Yes, I'm very frustrated that I've left AA sitting there, but like I said, I ran out of time. I ran out of money, so money's getting sorted out. So we're getting the time sorted out too. But yeah, I haven't touched AA in a while, although I left it in a reasonable state. It's not running, but it's left it in a reasonable state in the sense of it's well along in where I want it to be in terms of an implementation, at least correctness. I mean, the so many fucking mistakes and backed in and backed out. There's train wrecks of dead things lying around all over the place that I haven't got to. But it's kind of
Well, I
marching
get that
forward
there's a
on
lot
test
of
cases.
little work, but if you're just thinking of a roadmap, like what's on the burn down chart of major pieces that are missing?
In AA, the handling of forward references and self-recursive calls. So every C programmer on the planet writes forward references to name structs. Almost all of the functional languages require you to say mutual letrec and list all the mutually recursive things in one shot. I thought that was always kind of lame. So I want to have them be same forward references as you get in C, but be discovered as a mutual letrec, as opposed to a sort of a standard letrec. And that means you have to sort of restructure how you visit the type information to close the cycle, and you get them out of the wrong order. So there's a place where you have to collect up a bunch of things. Just like I can see, you collect a bunch of things and then you sort them out after the fact. Well, that's where I'm sort of at the moment. I had it going in a AST form, and then I was restructuring the AST and then dumping AST and SSA into C of nodes. And I have a C of nodes, direct to C of nodes version that doesn't do the restructuring the right way. And so I was trying to get the direct to C of nodes do the right kind of restructuring. And that's where that one is. Once that's done, I think the AA stuff is kind of, I could go ask now. I left it long enough. I have a source there. No source. What do we got here? Test. Just was doing an obvious set of tests here. Test stable. Right. A lot of these are just working. It's the evil mutual letrecs that were failing. So I could show you some things that are working and up to where I got the failures from. I think it's down to, here's the canonical bad test case that is my current failing that I want to work. Go find the docs again. This is like some really hideous thing. So let me go share and see kind of what the grief you're up against. See if this works. So A is declared as a function which takes an argument, does a random choice of calling B or returning it. Okay, D is randomly picks B or C with some ints. C returns A, B returns C. Oh, just a mess. Well, if you call D, then B and C polymorphically, self-recursively call A, C, and whatever, and eventually you come around to, you get a random int from 1 to 2. And if you call C, it's also polymorphic, and you get a random float out of the C call. So this should return me a pair of an int and a float, or even a small int and a 3.14. And the mutual recursion confuses the direct to SSA format at the moment. And then that's where it's currently at. It's all polymorphic and it all specializes. So in the end, the code gen ought to turn into D is a random pick 1 or 2 and ignores all the random identity calls that are just picking left and right identity wise. That should all fold up. Same for C, just returns you a float directly. It's like computable straight from the types straight up. So it's fine. Anyhow, that's the current failure. I can pull up some maybe interesting cases that are working that are obnoxious to read. Do we really want to show this off here?
And by working, you mean compiles, not
It compiles. Yeah, nothing's running, but the distance from it compiles to it runs is much smaller than the distance to it compiles. Because of the fancy things I'm playing around with the typing system, I have this long distance from it. It parses to it compiles. From it compiles with a correct SSA graph, getting an evaluator out of there. I mean, I looked at what Zamilia or Nick did. It took him like a couple of days, maybe a week tops. And it's very straightforward. Now, from there to good code takes a little bit longer, but I've just been doing another project, a complete from scratch compiler on the SSA form, on the CFNodes form, and that doesn't take that long. So the distance to CodeGen from here is it's actually pretty small. So this was the ugly one. Here's some kind of thing that works. This one's obnoxious to read because it has this nasty dot underscore, which is the overload. So this is a pair. So friends here makes you, it's either a value, either make it a pair or tuple, or you're doing grouped expression evaluation, sort of standard things you get out of a pair of parens. So here's a pair. It's a function, takes x and y, calls bang and multiplies. Here's the other half of the pair. The function takes x and y, does something with x being a float times y being a bang, which is really a integer result. Bang returns me true or false. Oh, I see, it's tab failures. That's what happened there. Okay. And then I picked the correct one of those two. That's what this was. Field load, pick the correct one. And you get passed in a float and a 0. Well, okay, so x being a float means you have to be this version, because here x is a float. So that all works, and he'll infer, that this is a float int arrow to a float, and he'll infer that this is int arrow int, and therefore you're
This
called with a
implies
float.
that bang is not defined on float with
No,
0
bang is
going
not
to
defined
1
on
and
float.
everything else going to false.
Okay, a bunch of people had bad sound. So Aaron, you said bang is not defined on float. This is true. Yes. So the arguments to the call are float and int, and only one of the two functions in the pair is of type function of float to int. So that's the one that gets called. So that works. I want to say somebody else was trying to say something and the sound quality broke up. No one wants to admit. Fine. Yeah, so type inferencing works in general. The field overload hack works in general. That's the dot underscore is my overloads. Most things are working. This one I end up structuring the resultant graph wrong, and then I have the moral equivalent problem that C2 used to have when the peoples went bad and the entire program evaluated to false and disappeared. Here, instead, I get self-recursive, mutually recursive types that are incorrect, and they infinitely, continuously unify, and the graph grows without, the type grows without bound. And so eventually I stack overflow in my type being vast, and it's sort of a bitch to debug now. So that's where AA got left. Other things all just kind of work. I mean, I have all the type inference on math, floats, signs, I'm not saying here, functions, pairs, and overloading. These things all just work. Yeah, fine.
And you still imagine that language as code just sort of shows up at a rep, not that you get the whole application ahead of time.
Yeah, I'm still able to run in a REPL. I'm sorry, I'm still intend to run in a REPL. The REPL currently is sick because I haven't touched it in 6 months.
Right. So if I start at the top of the file, I'm just working my way down,
Yeah.
compiling things. If I
Yeah,
have a
and-
forward
and-
reference, just
and a
nothing
big-
runs until the forward reference resolves.
Right. It's just like Python. You just start executing code bit by bit. Now, I'm torn what to do about imports in large projects, because you kind of want to have this import mechanism that says I can tell by looking at something about the file, who all the dependencies are, and then I can run all my dependency analyses things that turn into like Maven file lookups and, you know, auto updates of this kind of dependency or that or whatever. There's a thing there where the Pythonist version where you run code to find your imports means you can't run these ahead of time import manager or dependency manager tools, because you have to actually run the code to find out what your dependencies are. So Python went down this path of, if you write your dependencies this way, you intend to actually only ever find them, you intend for them to be obvious to every, you know, modular tool out there. But you can still run code where somewhere in the middle of a deeply nested if, I compute a weird hard path to a funny dependency, then I pound import some awful thing that I did on the fly. That's like Java's class for name. It's useful. I don't want to not have that. So I haven't decided what to do with what's the right way to do imports in AA yet. And why is Zoom telling me it has a notification? Probably because my chat window. Oh, why bang through to false? Yeah, right. So why did I say floats don't do bang? You know, I could go there. I don't care. It's less commonly done. Like, if you're testing floats for 0, you're probably broken already. People do float math, they're doing weather simulations, they're doing particle evaluations or whatever they're doing, you know, I'm simulating how to build a dam or a bridge or whatever. You almost never test for null or 0. Why? Because the answer is
You'd
never
rather
0.
people
The
just
answer
check
is,
that it's less than a billion.
right, yeah, the answer is you're less than some tiny epsilon. Yeah. So I think I'll live with my current theory that bang doesn't work on floats. Same as I'm not going to have Zor work on floats. I could convert all of them to an int and then work on them, but if I don't want to convert a float to an int automatically, I think that's trouble. All right. Somebody else's turn.
Hi. So I have a question that so preface, I might sink like 4 years of a PhD into this, but yeah. So
There's
I mean,
a lot
my
of
own
PhD
time,
students on this.
yeah, my own time, not someone else's time.
Right.
But
Okay.
so suppose I wanted to build an auto-parallelizing compiler and wanted to use the sea of nodes as the representation for that, but the thing is, I want to compile down not to like a parallelizing machine, but a parallelizing interpreter. Do you think that's possible? Because half the people that I talked to said that OCaml and Haskell have parallelizing combinators, but they don't work very well. So your
Right.
project is not going to work well at all. And half the other people said maybe it might work. So yeah.
Right. I think that's a hard road to go yet. It's kind of a funny one that is worth exploring at some future time that I haven't done. So I know that I can go bottom up and well, there you go. So Aaron says yes. I know I can go bottom up and discover loops, make them well structured, discover that they have large trip counts, unroll them, unroll and jam, do all kinds of scalar replacement optimizations, all optimizing for the case of a fast single-threaded piece of hardware. But if you have a large amount of work that you know is parallel to begin with, you don't want to forget that by throwing it into a low-level sea of nodes. So you could go to a high-level sea of nodes, and maybe Aaron can say something about that. I haven't done a high-level sea of nodes where you had whole block transformations done as a singular node that then understood how he had recursion internally, and he would collapse, you know, matrix multiplies can be reorganized in an optimal way, but you don't want to lose the concept that you got a matrix multiply or discover you wrote a matrix multiply the hard way. So Eric, do you know, can you say something? I'm not the person in this group making a chip. Yeah, well, the chip guy, yeah. Okay, so I can say something about what Darren's work is. You're talking about Derek's work?
Yeah, I'm talking about Derek's work. He's
Yeah.
compiling down to a parallel chip.
Right. So they're starting from a high-level representation that has nothing to do with anything sensible. They started trying to do like mid-level LLVM, whatever the MLIR, whatever. They backed off. I think they're working on that in the background. They're mostly hand hacking the loops until they get it down to a well understood single node parallel, and you can do SIMD on it. And then Derek's and I is picking up the SIMDizable, and we're breaking the SIMD parts onto the the AI execution piece of the chip, the GPU-ish thing. It's not a GPU by any means. It's really bizarre. But it's super tiny silicon, and so it's replicated a bajillion times on this chip. There's unbelievable counts of these things. And so you're doing, yeah, not quite. H2I had a higher level API. Like the API for doing big parallel work, the H2 API was a decent one, honestly. Now, what Derek and I end up starting with is, here is a SIMDizable piece of code. And we tell you the arrays you're SIMDizing on, and we tell you, at this point, they're baked down to like constant sizes. Because we will execute until we get to other constants at runtime, and then we'll do the things with them. And then they're, jitted down to the bare processing elements with the driver code sitting beside it. So we're doing kind of sort of like what a GPU graphics driver does, right? He takes some input description of a large parallel graph structure for doing, GPU, it's display things. We're taking something a little lower level than that, but not hugely lower, and turning it into machine code to run on the individual elements. And actually, not us, somebody else groups the individual elements. Like each SIMDizable chunk we're looking at has like 8,000 wide, but there are many, many thousands of these things on this chip. So somebody else is doing the layout on the chip at that level, and we're picking it up at the next layer down. If you were to do, for your PhD, if you were to do this, I would look at, and you wanted to play with sea of nodes, I would look at putting nodes in the sea of nodes that did large parallel math, and then let the standard optimizing hacks sort out your large parallel math transformations that you do to like optimize your life. And then at some point you declare you're done doing large parallel math transformations, and you lower. And you take your big fat nodes and you explode them out into nested loops. And then the other pieces of sea of nodes that are sort of well tested, turn that into good code.
Let's phrase the question the other way. What are you trying to do?
Yeah. Okay. Thanks for the advice. So what I'm trying to do is like take a general purpose programming language. That means not like a math or array description language, and parallelize that to some extent, like reorder operations and all that. And the thing is, I know that doesn't work for high-level languages normally because there's too much undeterministic information that you can't statically analyze. But if you JIT compile it, you probably could, because as you lower through you gain type information and type feedback, the sea of nodes becomes a lot more, mobile. So I was thinking, like, is that possible with a high-level programming language like Java or Python?
So you're missing a key piece.
Mm-hmm.
And that is, you need profile data and a runtime.
Yeah.
And then,
Yeah.
then you're heading for a JIT. Once you decide you're heading for a JIT, you want a fast compiler, and then you can make sea of nodes go really fast. Simple is not making all the choices for speed in order to be a tutorial, but you can obviously get it really fast. Okay, fine. But that lives in this context, the fast JIT lives in this context of, I have a runtime, it has pieces of code that are running, it's collecting profile data on it. It can stop some piece of code and redirect the execution to another piece of code with semantic equivalence, but presumably much faster performance because you discovered something. The tiny loop got unrolled to the limit and completely eaten up by the optimizer as part of the bigger loop of the giant thing, which you then distributed and parallelized and split and blah, 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 whatever you're gonna do with your, big guy. But you have a runtime. The runtime is as complicated as the JIT.
Yeah.
And I don't see a lot of good runtimes that you can pick up that carry the right things and let you do the right things sort of for free. that one seems like it's still not a well-solved problem. Sorry,
the
go ahead,
runtime,
Vivo.
the runtime for Bolin, I was trying to keep it small and it grew quite large. And you guys remember how large Boost was when I
Yeah,
told
but
you
you ain't
guys how
nothing
many
compared to
millions.
Hotspot.
Yeah. I was kind of wondering, were you asking how to make things parallel in OCaml, and you're afraid that it was going to be hard to implement since it's such a high-level language? Was that the question?
No, I just referenced OCaml because they have parallel combinators, or was it Haskell? I forgot which one. And the thing is, the people in OCaml land have tried for quite some time to automatically parallelize high-level programming languages. And like a lot of people told me that the efforts aren't really like that impressive at the end. Like the results aren't that impressive. The efforts are impressive, but the results are not as good.
Yes.
Yeah, sorry if I offended any OCaml people.
No.
Yeah.
I don't think there's anyone's going to be offended by saying what it is. I will say that I had a great time with H2O as a parallel programming model. It went a long ways. It did a lot of cool shit. That's not a terrible place to start from. If you then start directly on H2O, if you do H2O theory, then you have to build your runtime. If you start with H2O directly, you're in Java. As soon as you're in Java, you have a JIT. And you can class for name all kinds of code. And your JIT can say, here is some piece of code that looks like a big ass bulk array operator. I have a generic implementation of Java. Oh, I have a specialized version where I basically class for name, clone the code, rewrote the bytecodes to put constants in everywhere. And I taught the JVM an optimized single version of something. And I did that in H2O. And we got, hot, fast inner loops of generic things. So big parallel generic operators got hot, fast inner loops with specialization done on the fly using the JVM.
Did your programmer tell you which of the things were the giant data sets, which of the things were the tiny ones, or you discovered that?
Discovered them. So what really happened was you would get a data frame and you said, do all map, blah, 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 whatever, run this function on this data frame. And we'd ask how big the data frame was, but this was at runtime, right? And if the data frame was beyond a certain size, we'd stop and look at the map call and say, look at the column types, look at the map call, make a custom version of the map where the column types were known to be the fixed known. We basically did code cloning with specialization. This is like doing data science. So you would have columns. It's not like neural nets where it's all just miles and miles of doubles. And now you want to have doubles be, F16, F8, whatever, tiny things. It was data science. So you have some columns were just ints, some columns were floats, some columns were strings. Some of the columns had missing values. Some were 90% missing. Some were a few missing. Columns had very strong biases. So the count of handicapped people versus the count of all people has 99 to 1% ratio. And so HO would compress them and you'd have these compressed formats for all these columns. You got this huge compression. Performance came because the data was giantly compressed and therefore you didn't run out of memory bandwidth. So one of the big wins for H2O was data compression turns into less memory bandwidth, turns into we run as fast as the CPU x86 can run on compressed data, which is pretty damn fast. But then the hot inner loop would take a vcall to unpack compressed data structures. So if it was hot enough, you'd clone a version that knew what the compression strat was. And he would inline the compression strat of choice and optimize that way. I see Theodore's like squinting his head on that one. You.
Yeah, I get the most of it. So you're emitting that code at runtime, emitting the bytecode?
Yeah. The two things we did was we emitted the serialization code based on profile analysis between cluster to cluster node members, and we emitted specialized versions of the hot inner loops that were specialized by the compression strats. And the node to node guy was also doing a compression strat where you'd hand me a Java class that you wrote custom for the problem you're solving, and you're gathering up your data, you're making your histograms or whatever, and we're auto-distributing, auto-parallelizing. This is this is H2O is doing auto-distribution, auto-parallelization on sort of simple Java code. So it's not quite simple, but reasonably straightforward, simple Java code, where you wrote the inner loop and then you'd said bulk synchronous parallel, do something with this hot inner loop. So that's sort of the style it went for. Along the way, you would have temporary data that would be passed from node to node. It had to be serialized. We had a custom serializer that would emit Java classes to do the serialization. That would turn into things that were clearly faster than the fastest serialization protocols I could find out there, whatever the fastest ones you've seen. So Google Protobuf like never gets close. Some of the other ones got closer to what we were doing. And you didn't have to annotate or mark anything. You just said, I made a Java class. I filled it with a bunch of data. And then for whatever reason, it went to another node. Like I put it in the key value store and the other guy loaded it, or I was part of the map reduce and it was a reduce step coming up with your results or whatever. So however you did it, you never said, you didn't deal with parallelism directly. You just wrote a class, you filled it with data. Somebody else wanted that guy, we serialized it. So it was very easy to use, very simple, and really fast. So it was always, as fast as your network could keep up. Usually you had decent networks. It was as fast as you could load things through the memory hierarchy. And the Java, serializer would basically read and write bytes in and out of a network byte buffer and inflate and declare you had a Java class instance on the other side. Like in a decent, fast internal data center network, you'd be low microsecond counts to move a structure across the wire. I did all that kind of things are useful there, caching, and gave you the Java memory model across elements in the cluster and stuff. It's a good base for a lot of interesting parallel distributed work.
All right, thanks.
Yeah. And you're doing a PhD, so you're doing something exciting and whatever you're going to do. If any of this stuff sounds interesting besides the code itself, you can ask me about experiences, because I've done a bunch of, like I said, related things. I didn't do HPC with it, but I did a bunch of stuff with H2O doing big data science. So HPC-like flavors.
I do still wonder what's the win of doing things in a compiler versus in a library. People have gotten really far. Things like NumPy, where most of your code is just.
Aaron, your sound quality broke up again. So say that again. Just some of you're very quiet and.
People have gotten very far with libraries like NumPy that just give people the ability to express their big loop in slightly different syntax than most of their Python code. What do you see as the big advantage of doing this in a compiler versus just having a library for it?
Right. As far as I'm concerned with H2O, you wrote your thing in a funny different syntax. The library was H2O. Now, how does the library implement it? Well, in H2O's
right.
case,
I was thinking of that more as a question for Ken as to what's pushing him in this direction of research.
Okay. Well, the main thing is that there's a lot of Python code out there that aren't loops. Like I know, like a lot of people say 90% of the time spent in loops or something, but I don't think that's the case. And I want to find a way to automatically make stuff that aren't loops faster. So not just loop vectorization or loop optimization.
Well, that's not parallel distributed scale out. That's you're optimizing Python loops.
Yeah.
Which I would say.
I'm not. No. In this case, I'm not looking to optimize Python loops. Like that's a pretty soft problem. You can use that number or something and JIT it away.
Yeah, I misunderstood what you're looking to optimize, or what your PhD thinking.
Yeah, it's a bit hard to explain right now. So I think
it sounds like you're looking for more general purpose application code, right? Like programmers writing function, calling another function, which maybe calls a map, which is going to be passed higher, which is going to be higher order function that is going to be passed some predicate. Is that what you're looking for?
I'm just looking for a way to. Okay, sorry, I just saw your message. I'm just looking for a way to like make the entire language automatically run on multiple
Yes,
cores.
then you definitely want to look into this heartbeat scheduling work by
Okay.
Sam Westrick and others, because especially this latest paper from Papul, Automatic Parallelism Management, they added this construct to a language, it's ML-based, called PAR, which expresses potential parallelism, and the compiler and the runtime cooperate to promote this to parallelism where it makes sense. So it's kind of using the runtime information to have very, very low overhead potential parallelism construct. And it's relatively new work, but it's performing pretty well. And this is general purpose. So this is exactly as you say, not just for loops, which are a very well understood problem for decades now, but for more general purpose programming. So I think that's very interesting work. I would look into that.
Okay, thank you.
The other two things I would recommend is looking at Dudley's fork join library and the way that JavaScript does its scheduling.
Oh, that's interesting.
Because historically we've had single-threaded languages just threw everything on the work queue, and then the event loop goes around and pulls things off that work queue, does it. But they tend to, JavaScript does it on one core. And then you've got things like fork join that says, oh, we've got this giant set of multiple work queues that are all stealing work from each other.
H2O uses Dudley's fork join.
I think you might be surprised how far you can get parallelizing stuff by
Wait,
just
sorry, can I have a
Fork
link
join's
to
a
that,
good,
please?
a good base.
As well as I encourage you to explain your PhD to anyone you can find who's willing to listen, because every time you fail to explain it, you'll understand a little bit better which part you don't know yet.
That is a great piece of advice. It will sharpen your thinking every time you attempt to explain it. And somebody will say,
There are a few
I
things
didn't get
more
that."
valuable to a PhD student than failing to explain your PhD to someone.
Yeah, yeah. Aaron, I think you have a lot of background noise. That's the issue.
Yes, I'm in a terrible audio environment this week.
Okay, fine.
Cameron's not here, but I know he would tell me to explain my memory management.
Yes. Well, I have asked many times, and you get so far, and then you stop. You say, it works for me.
Well, the thing is, people can't articulate why they can't understand. So, am I supposed to guess what is
Yeah.
hard to understand to
Or
other
you
people?
ask what you don't understand. So for me, the canonical example of what I don't understand and why I think there's an issue is I'm waiting to see you write a general purpose hash table library. And the memory management in that library is all about long-lived data that is not related to the rest of the program per se. So it doesn't have scoping that's related to the program. It has to live in its own scoping and collects things. I haven't seen that hash table come around, even a bad version. And that makes me wonder.
Yeah, I remember you asking that, and I remember you wanted a real implementation, not like a pseudocode.
Right.
And
I wanted to see the compiler prove whatever you need to prove to get yourself to compile.
That's different from explaining, but yeah,
well,
I remember that.
But the point here is that the existence of that would tell me, would be the explanation for me that works. Right? Like I think that what I hear you say and what I know to understand about how memory lifetime works, they don't jive. Unless you make some very conservative approximation or conservative assumption about your memory, which limits your use cases to the point where things like, I want to say, even a vector now, so a resizable array, where the lifetime of the backing array exceeds the lifetime of the caller, typically.
I can probably explain through C++ code, but I don't know if you would accept that.
C++ allows this because malloc and free essentially go to a global pool, have global scope. So you said I have Bolin does automatic memory management. I want to see the automatic management work with a thing whose lifetime is not stack scoped or scope-like.
See, a lot of it is like that. That's why it's easy to do. Like, I mean, that part is easy to do because
which part is
the
easy to do?
If you know the stack, I mean, if you know where it lives on the stack,
right?
And
if you have a
know
scope
everything
lifetime,
yeah,
right.
And then everything that uses it has a smaller scope, then it's that simple.
Right.
Like
that one I don't have any trouble with. I'm asking, how do you handle things where you don't have the stack scope?
Yeah, that's a lot of ownership keywords that are left to be implemented. Yeah.
Okay, so you
You-
can come out and say, I don't handle them.
Mhm.
And then I'm going to come back to you and say, okay, I think this kind of memory management where you only do stack scoping is not something that I currently want to deal with. I think of things that have longer lifetimes or outside of stack. And so that's a fine explanation, but that's not the programming model that I'm looking for.
If I'll probably have to talk to you like off of CCC about like some example code, because I think I need to see some like Java or C++ kind of code that is targeting the use case you want.
Yeah.
Because if I can see the use case,
Java
then
array
I can Java. Yeah,
Standard.
but though the style I have is probably very different from other people, so it fits my style like, easily. But that's because I've been dealing with memory management for so long and know how to write things in a certain way to make it easy to deal with.
Okay,
Try
so
porting concurrent hashmap. That is a specific piece of code that you could try to port to Bolin and see what happens.
yeah, concurrent hash map has another layer yet. Like array list has a lifetime for the backing array that would be equal to the lifetime of the array list itself, except that you keep rotating new backing arrays, but they all have a lifetime equal to the array list itself. So that one's sort of the first step up.
Yeah, so the stream kind of falls into the same category, a stream. So
Yeah, right. Yeah, yes. There's some lifetime for the original guy. And Rust, in theory, I think handles this kind of well, where you pass along some sort of lifetime management
Yes.
discussion.
I believe you have to annotate it. But,
You have to annotate the hell out of things in Rust, which I don't like, but there you go. But you could claim that if I'm making a vector, a VAC, a C++ VAC, that the lifetime management is the lifetime of the VAC, okay, and then I have to declare that have a scoped-based lifetime, and then you get in the library question: what is the scope of the things that the library has to deal with?
I think Levo is asking for the client examples though. So you are giving the library example like parallel for concurrent hash map, okay, but probably you want to give some example use cases. This is the canonical application using concurrent hash map 1, 2, 3. So I think that's what he's looking for.
Yeah, or the canonical
Correct.
use case for a hash map is to do caching of asynchronous requests. Exactly, concurrent hash map.
When you guys say hash map and arrays, I'm thinking, oh, you just hand the ownership to the array, and then the array is the one, or the hash map is the one that has to deal with like deleting the memory. But it sounds like that's not what you wanted. You wanted the array to provide you the data, but you don't want it to own the data. Is that what I'm hearing?
Yeah, and I can translate between the two words, because I think, Levo, you are thinking similarly to how I'm thinking. You are probably not using async very much. And if you are using async, you are probably following the structured concurrency approach, when you still have something similar to scope-based ownership. But in languages like Java, well, only recently they added structured concurrency to Java, but before, async was just a mess. And it would be exactly like Cliff says, when you don't have any kind of scope that could express the ownership graph, and every part of application could read through this in principle, and every other part of application could write through this concurrent hash map. And that's why you run into this problem when you have very unstructured lifetime management. You cannot express it as a scope at all, and you have to kind of annotate or buzz the information. But it could be, the interesting outcome could be that maybe this is a problem you do not have to solve in your language if you can provide very good support for async structured concurrency. But I think this may be still a hard problem, because even Swift, which has done quite a lot of this, does leave a way out to have unstructured concurrency in async. So probably if you want to look at those use cases, look for people using async without structured concurrency, then you should be able to find some use cases that would be unaddressed.
It kind of sounds like Cliff is asking for a use case that uses shared pointers, and I'm trying to avoid shared pointers as much as possible.
Not even shared pointers, but when you don't know anything about the termination and creation of a task. Again, unstructured, because in structured concurrency, usually you have some parent task, and then you have some child tasks, and this doesn't have to do anything with the scope as in control flow scope, but you have like kind of shadow or parallel structure so that you know, for example, if the parent test terminates, you want to kill all of the child test. Yes, fork join is a special case of the structured concurrency, but there are many more cases when you have any kind of task graph, when you can hierarchically describe the relationship, and then you can guarantee so you know something about the termination. So it's the lifetime scopes that are nested in each other. It has nothing to do with the scopes as in the source code scopes, but
Right.
it's still very
yeah.
similar.
Like
Cliff, I
H2O
think
did
Cliff,
the
I think
model
my
where-
answer is going to be you're going to have to. I'm going to force you to structure your code a different way. I'm trying to avoid locks and so many other things in my language.
So
Yeah,
force-
it might have to be different.
forcing to rewrite in a different style is okay if you can cover the interesting use cases. So uninteresting use case is the one that says I have a web server, it takes asynchronous requests. I'm running many threads in parallel. They all make DB requests. The DB requests are cached locally. I have a concurrent hash map caching. The lifetime of the concurrent hash map itself is the whole program. The lifetime of things that it's caching now become the whole program in case another request comes in that's identical to the first one, but because due to round robin DNS or whatever the hell, it hits a different thread. And so it's not lifetime of a thread that's serving requests. It's a lifetime of the server. That is an interesting case. And then somebody said the other interesting case here is that the vec, the hash map, whatever, it has a array internally. The array internally does not own the lifetime of its contents. It's merely handing it back as a placeholder. It's a convenient sidestepping place to hold things. But the program on one side calls into the hash map and hands it data. Later, it gets data back. The lifetime of the data is the lifetime of this program, and the hash map is not. It can be within the lifetime of this guy, but he doesn't own the data he's holding. He's just a placeholder for the moment. Does that make sense?
Yeah, it does. I just think it's going to be a long explanation, and I'm going to have to like prepare or something.
Well, like I'd love to see the examples and or how you solve these problems, where you can say, here's my hash map. It came from a library. It will hold my data without owning it. And now I want to annotate the library to say, you don't own the data you're holding. You're going to somehow tell the other guy, the owner, when you want to let go or do something with it. And the owner says, here's some data. And then the owner says, oh, the data is dead now, get rid of it, or something. There's a thing there, right?
See, the easiest way to do this in my language, like the way that you don't have to annotate so much, is you say either the hash map owns nothing or it owns everything. And it sounds like you want the nothing case, which means you have to be able to guarantee that the stuff that you put into the hash map is only going to be temp or removes by the time you're ready to clean up.
Yeah.
So I prefer having the hash map own things, but I guess I can like try to figure out like the easiest, like
Right.
the less intrusive way of like saying I want to insert things, but it has to be removed before my lifetime is done.
Yeah. The program owns it, but he's pulling in a vector to hold things temporarily. And then the vector has things he doesn't own, but the vector can't. Well, the vector could go away and say, I'm gone. I don't, because I'm not own it. I just disappear.
Because the way I was dealing with this is either the thread owns the hash map, but that's not going to work in this case because you want it to be shared across all threads. And the other way was use a memory pool, but then the memory pool owns it, and and I don't think that's what you want either. So,
Well, if this was easy, it'd have been solved a long time ago.
but why don't you want the hash map to hold on to it forever and be the one that controls how long the data lives?
Oh, because the hash map in my head has no. It itself has a lifetime, but it's not the owner of the data. It's a convenient way to go find something from something. So I'm parsing code. I have a symbol table. The symbol table match symbol lookup strings to IR pieces. It's a hash table. Now, what's the lifetime of the contents of the hash table? Well, I don't want oops, Aaron dropped and rejoined. I don't want the hash table to have to claim I own the mapping from string to IR. I don't own the strings and I don't own the IR nodes. The parser owns the IR nodes. And eventually he'll hand them off to a program graph object, which is part of the compilation, which will own the IR nodes. Hashmap never owns the IR nodes. He's just a temporary side place to go do the string to IR node lookup. And as soon as the parser exits the scope, that piece of hash table goes away. The IR nodes don't go away. They're still owned by the parser. The strings go away or not, I don't care. They're unrelated.
How would you feel if the hash map like has everything as a weak pointer?
Well, so weak refs imply a GC, and Matt said that, or Aaron said that, but like weak refs are a most miserable story here. You do not want weak refs. If you want to, I can go you war.
No, I know with threading you don't want it because then you're gonna have to lock to make sure like something that's holding on to it.
No, it leads to this model where if a GC cycle happens at any particular point, the ref can disappear unless you have a strong reference to it. And what this means is you randomly get things to disappear about when a GC cycle happens. And if GC cycles are rare, the bug lurks for decades because you don't ever see it happen, except randomly somebody crashes, they get an NPE out of the blue because they got the GC cycle that deleted you ahead of time. If your name is Azul and you're running GC cycles every few seconds because you can, because it's easy, then suddenly you get this bugs all the time. And everyone hates the weak refs because, you know, I make a thing, I put it in the hash table so somebody can find it. If I do the wrong ordering, I make it, it's weak immediately upon construction. I need to hook it before I hand it to the hash table. But if I hand it to the hash table and the hash table has it weak, then I hook it, too slow. Hash table GC came, wiped out of the hash table. So I just put in hash table, the very next clock cycle, it is not in the hash table. It's just like a bad programming model.
Yeah, no, I definitely don't like it. I was just asking what you thought of it. Because the other issue is like if you don't lock it, you're gonna have to like know if someone's still holding on to it, which means like you have to pass in a lambda. And I just
you don't have to pass a lambda. You have to have a way to say it's alive. So ref counting is a way, right?
Yeah, and there's no GC, but if a thread is over and I want to mark everything inside of the hash table that it's like it's not pointing to a valid memory anymore, then like I need to make sure no one's holding on to that because I don't like it. I was just like wondering.
Right.
I'm trying to think and I'm guessing strong references you don't want.
I mean, you can also look at the memory reclamation strategies that are used in lock-free programming, like RCU in the Linux kernel. That is fairly complex to implement to some extent, but that could also be a way to approach the problem.
That's why I wanted the hash map to own it, because then it could just do that. Like it's much more simple.
In my parser example, the parser scope exceeds the scope of the hash map. Parser owns the IR. Parser owns the hash map, right? And then you want to tell the hash map, you are not the owner, and your lifetime is nested within the owner's lifetime.
But here we're trying to figure out who will live the longest. It's not like in Rastrack who owns who at what point of execution in time.
You're trying to write code such that the compiler can prove you didn't screw it up.
Yeah, but by proving that these things outlive these things, so therefore it's correct by the end of the program. Won't be easily for reclaiming.
Huge annotations.
Without
Cliff, so you don't want the hash map to own it because is it messing with your memory model, or do you have another reason why you want the thread to own?
The reason nodes? I don't is because conceptually it's not the right answer. I have a parser. Parser starts his lifetime. Parser begins parsing. He builds a hash table. There's a hash table. So lifetime of the parser is this. Here's a hash table. Okay. Parser builds nodes in an IR and string node mapping, put them in the hash table. He reads and writes and reads and writes. He ends a scope. This hash table wants to go away. The IR blob he's building is going to outlive the parser. It's going to become part of the compilation unit. So the parser is going to start, build a hash table, and then delete it. He's going to build some IR, and there's a compilation unit to fit my monitor. It exceeds the parser. There's a parser, and then there's a cogen. So parser is going to build IR, hand it to the cogen side. IR lives this long. Parser lives this long. Hash table lives this long. Hash table refers to IR that's all through here in lifetime. So the
Shouldn't that
lifetimes
mean
don't.
shouldn't that mean that the hash map owns nothing and
Yeah,
you don't?
it owns nothing.
Yeah. So then what's the problem? Because I thought you said you can't know that the hash map outlives the thread. or
So
the
in that
node.
example, I tell you that the hash table's contents outlive the hash table. So I want to own nothing. But is there a general strategy? So I can come up with another example where the hash table does own things, and then it wants to free or delete. So I'm a caching strategy. I have a finite sized hash table I can cache. I have an LRU strategy that the hash table is responsible for, and the hash table is like weak refs. Hash table declares, oh, I'm not going to cache this thing anymore because it's been around too long, so I'm going to throw it away. That means the hash table owns, and the hash table throws away when he declares your LRU sucks. You know, it's too low. I haven't seen this in a long time. I'm stopping caching.
Okay, there's too much to put in my head right now. So I think I gotta write this all down and then go through it like one by
Right.
one and then
Okay,
explain it.
I'm trying to do let me do a share here.
I definitely need because you definitely need like one hash map for one use case and another one for another use case.
Well, maybe that's
But
the
it's
answer.
totally yeah. That's the way I was like thinking, because you either wanted to own everything or you wanted to own nothing, or you got to go into like a land that you don't want to be in where there's like locking and references and all that. Like I'd rather not do that if it's possible. Because I do have a case for HTTP, and I do have another case where you just don't want the hash map to live it for very long, and one owns, the other one doesn't. But yeah, I think I just need everything to be written down to like answer properly.
So I tried to make a thing here where I show scoping. There's a compiler, there's a parser, the parser builds a scope. The scope has a hash map. The compiler makes many of these. That's a cleaning star. Makes many of these scopes back to back to back, where the hash map doesn't own the IR. The IR is owned by the compiler. The hash map lifetime comes and goes. So
I would imagine that in this case, the hash map owns nothing, and it's expected that the compiler will clean up the IR.
So in this, right, so hash map owns nothing is a good way to think about it. And
Yeah.
some other notion says the IR array and the IR nodes that go in the IR array are scoped by the compiler.
But
So
inside scope, the hash map can manipulate the IR. So
yeah, he certainly, the parser's creating IR nodes. The hash map probably isn't altering them directly, but the parser will extract an IR node from the hash map, manipulate it, and put a new IR node in or out or whatever. The parser is creating IR nodes and manipulating existing ones. So then there's another, let's say, an HTTP server.
Just hold on for a sec. This example that you just wrote out, you can clearly see that the hash map is inside of a scope, which is equal to or less than the IR array.
Yeah.
And the IR array is like higher up, so you can think of it because in C++, whatever you construct first is what you deconstruct last. So basically, the way that you wrote it out is like all the Bolin has to do is to make sure that the IR is owned by the IR array, and then that lifetime is always going to be greater than the hash map. So like it's very simple check.
So you have a hash map whose ownership is it exceeds the lifetime of the hash map, and you have a way to express that in Bolin.
Yes, this would be the hash map owns everything.
And for all CPU's new thread, might as well say for all parallel or whatever, parallel 20.
I'm assuming that the hash map is technically like a LRU.
In the parser case, the hash map doesn't throw things out. The parser manages the hash map's lifetime by declaring dead or alive. In my HP server case, the hash map lives here, but he has internally an LRU behavior.
Yeah. Okay. Yeah. Good.
And on every put, the shared server, put is a function which takes a request and, check strat. Does something, put request here or something. It does something like this where he says, if you're doing a put, see if I'm full, delete something. So I owned the DB results. So here, this makes a DB result. The res is a DB result, but the lifetime of the DB result is the lifetime of the entire HDB server request. And the hash map has the rights to delete it. Or you could say the lifetime of the DB result is the lifetime of the shared cache, which happens to be the lifetime of the server. And the hash map now owns the DB result and can delete it. So here I want the hash map to own it.
Okay, so the syntax for this is a little bit harder because essentially you can't delete things while one of the threads has the data like taken away from it. Like you don't want to delete something that's in use by one of the threads or the one of the requests.
So okay, so then you have this funny game where what is I want the hash map to drop the request, and now is it unused? So dropping the request of the hash map's easy. I just don't find it again. In the land of a garbage collector, he discovers unused and deletes it. If I want to do an automated lifetime management, as soon as it leaves the hash map, as I delete it out of the hash map, I'm very excited about how many currently existing requests and now how you do that. It's like a LRU based, not LRU, ref counting, atomic ref count updates or something. There's some lifetime management.
Yeah. Okay. So this is the harder case. So the problem here is how does the hash map know if you're still using it or not?
It doesn't.
So you would have to like there's no syntax to say okay, technically I can have something that's kind of like RAII, where when you take something it will tell that the hash map that you're done using it, like some kind of not like a lock, but just like a destructor that will call the hash map, says, okay, I'm done with this object. You can clean it up if this is like queued to be cleaned up. Or the alternative is you can, when you ask the hash map for data, you can pass in a lambda or some kind of like, you can pass in something, and then it will on exits, it will check if there's anything queued to be deleted. But in either case, it just sounds like hard because you just got to figure out like what to delete and not like go through all the memory and seeing because a lot of there's going to be threads that are asleep if you want like if you want green threads.
And again,
it just sounds like a pain in the butt.
I would once again say this is generally going to be a hard problem because you will be solving the automatic memory reclamation the same as you have to do for log-free programming and C and C++. So if you look at this RCU protected hash tables, they're solving the exact same problem. Hash tables have multiple key value entries, right? and one thread may be working on one key value entry, and the other thread may be deleting this, and there may be an overlap. So it is your problem to solve to prevent this deletion from taking effect before the working thread is done working. But this is a solvable problem. This is called automatic memory reclamation in general.
Yeah, so the first hash map for the compiler, that's just a hash map. The HTTP one, that would be like a concurrent hash map, and then this would involve blocking or locks
No,
and
no,
blocking.
no, no,
No.
no.
You don't want that?
Remember, look into lock-free memory reclamation.
Yeah, yeah.
You can
Concurrent
have
hash
lock,
map has no locking.
you can have lock-free algorithms when you have multiple threads working on the same hash map, and they may be doing completely unstructured removal, insertion, and
Yeah.
deletion, potentially stepping over another, and you can still make it work.
Right.
That's called memory reclamation. And it can be done in lock-free algorithms.
Okay, so non-blocking hash map is,
RCU is one of the examples.
yeah,
So what happens if you have a tiny hash map and all the threads are using all the data and someone wants to insert something, but the hash
You
map
may
is
have
full?
to do something like generation counting, for example, when you count which generation of the hash map you are in, and if every thread, whenever the threads are moving on, you may be able to increment the generation counter, and it tells you how long you should be holding on to a version of the hash map. It's a very butchered explanation. You can't really explain this in 5 seconds, but
I mean, I can pull out the non-blocking hash map code and slides and shit. There is totally a way to do this. And-
So how does it know that's not the other thread is not like using the data that it wants to delete?
Okay, so break out the problem here. Non-blocking hash map will totally handle the case where 1,000 threads all do puts at once on a tiny hash table, and he has to grow the table.
Oh wait, hold on. I forgot to ask this. Would this be under a GC or not? Because that affects the what I'm
Right.
thinking.
So the implementation I have of non-blocking does use GC. It does not need GC as in a general theory.
Okay, because I was explaining how to do it without a GC. So,
yeah, right, without GC. So
yeah.
there is a version of non-blocking hash map without GC that handles itself internally for growing and shrinking the table. Separately, there's a question of the themes that are in the table. What is their lifetime? The implementation of non-blocking hash map I have has no clue about the lifetime of the keys and values that go in it. He only understands his own internal structure lifetime.
Well, the issue I'm having is what happens when it's full when you try to insert things, and how do you know if something's been checked out by a thread?
Okay, so you don't know if a thread has grabbed a member, because I mean, you could put one in and then you could hang on to it, and just so you have a number, you have a key, outside the table and a key inside the table, or a value in or out or whatever. That's not the problem getting solved by the concurrency part. Non-blocking hash map handles the table grow situation differently from Java's concurrent hash map, but both are totally valid. In either case, somebody comes along and does an atomic update to get a larger structure that the new values need to go into. So there's atomic updates. So not locking, but atomic updates. And then however the guarantees are made such that every put happens, doesn't get lost, and everybody can find things in the end. And some efficiency happens. So if you have some temporary thing in the middle while you're busy hacking, it all works, but you clean it up and you get back to I'm just a normal hash table, which does a hash and a lookup on an array, and it all works.
So what is your feeling about if what if I just made all the entries be a shared pointer where whoever holds on to whoever last decrements the counter has to free it?
So
How do you feel about that?
you just said counter, and then you're doing ref counting. That is a strategy that knows to work. But atomic concurrent ref counting has expense issues. Although Mark Falco's not here, he got a good version that made it fairly cheap to be multi-threaded atomic counting.
Because this problem,
I mean, the
would
hardware
have to,
tries to help with that.
How? Yeah, oh, you mean it's
Atomic increment,
counter?
atomic decrement.
Atomic decrement? Maybe. It's one of these things where it's still so expensive, you want it to be fairly rare. So Mark Falco's solution for atomic ref counting said, I just have a bit that says the ref count is known to be held by multiple threads. And I can do something when I know that I'm deleting myself and there are multiple threads. I do something expensive to force some other thread to deal. But if I'm just doing local updates on myself, then I can keep my local counts and all other threads recognize that there is another thread counting on it. He had a way to break apart I'm doing local updates myself. That's not atomic. When I'm
Well,
down to 0 myself, I do an atomic thing. If no one else has it, I'm responsible for deleting. I delete. It's good.
Yeah, we implemented something like that in C Python recently, actually, because we found that atomic reference counting had too much contention that
Yeah.
it wouldn't scale at all across multiple threads.
Yep.
so yeah, I just need to understand the constraints better because
Okay.
like I can understand how to do this if we're using like counters, or that's easy. How to deal with deleting things when you don't know when things are chat outs, that's another story. That's why I like
Livo, I share the thought, look into that. It's on this concurrent deferred reference counting, smarter atomic smart pointers.
Throw links into the doc, please.
All right.
yeah.
And same for Ken. If you got a link to biased reference counting in
Okay.
CPython, if there's a link to that, throw it in the link section of the docs.
The way I would prefer to do this is you have to tell the hash map that you're grabbing data and you're done with it, and that's I can write syntax for that. Like that's not going to be too much of an issue.
Right.
The problem is what happens when it gets full,
Okay,
because
so
if I can always grow, then that's not a problem.
yeah, so suppose you can always grow. That's a solvable problem.
Okay, then that should not be too difficult.
So
The
here
hash
I've-
map
in
the
the
concurrent hash
example,
map would have to hold on to. I would just have to know if something's checked out or not, and then
And I mean,
uh,
you only
yeah.
have two choices for the full hash table: either reject the request to insert or block indefinitely on the request to insert. And I claim this is it.
no, non-blocking hash map doesn't block.
No, but when it's full, it's full. So either you reject the request
No,
because you
don't block. You grow, and grow means I allocate.
you allow for block. Okay, if you allow for allocation, then you're living in a completely different world. Yeah, that's
Yeah.
fine.
Yeah,
So
that's
right,
why I was saying block earlier. Yeah, okay. Yeah, if I can always
I'm
allocate, then
claiming
sure.
common everyday hash tables that people want to use all grow. It's too inconvenient to pre-size your hash tables and be wrong. So they all grow. So start with the knowledge that you're going to grow. Now the grow can be made atomic, multi-threaded safe. Okay, fine, it can. So now the hash map grows without bound until you run out of memory, actually. But that only happens if somebody else is broken.
Yeah, so the way I would just do this is to have either some kind of an object that says once this object, this is like hidden from you. So when you grab the item, this object would just be in that scope, and when you leave the scope, it'll just say like that the reference that you grabbed from the hash table, that's not going to like exist anymore. Like there's no it'll call the hash map and say this thread is done with that entry, and then the hash map can mark that it's not in use. So potentially later when it's cleaning things up, it can remove it.
So this is ownership.
Yeah, this is an ownership callback. Like I've highlighted in blue in the code with the lifetime of res for a random thread. But when that random thread is done and he wants to go tell the hash map I'm done, the hash map has to handle concurrent callbacks that say this lifetime is done, and they're concurrent on multiple threads. This gets into the atomic increment decrement issue, which has heavy contention issues and how you efficiently do reference counting, basically.
So the reason why I hate atomics is because I use them. So I can write this code, but I just it's just you just hopefully things are not banging on the same reference, and it's constantly
let me
turning on and off.
Find let me find the better version of non-blocking hash map.
No, don't worry about it. Like I can, I understand the problem now. Yeah, there's a way I can deal with it. It's just not the most fun way. Like GC is probably easier for you guys, but like when you wrote DB result, it would actually be like handle or not handle like a wrapper around the DB results, and then when the wrapper goes out of scope, it would just ping the hash map to say, okay, I'm free this object, or I mean this object's not in use. Yeah, it would just be like
by
a lot
wrapper,
of
you mean that the user should wrap it in an object that would signal to the hash map, or you will insert that yourself, the compiler?
Well, we call it the structure, which then will do the writes.
Okay.
It might be just a few instructions, so it's probably going to be inline, but yeah.
Yeah, let me throw. I have a better version. Let me go throw a link into this. Non-blocking hash map. I have a bad link here.
A lot of my strategies is just to use a memory pool. Like, it just makes things so much easier than it can deal with. It'll just free everything at once. It's pretty nice.
Right. The problem with pools, well, maybe you can grow them too. You don't want you don't want to be a fixed size pool, because then you just die when you hit the size limit. And you don't want a vast pool, because then you can't do anything else, because one pool eats all the memory even though it's not using it.
I do remember looking at your hash map, how you would after a certain amount of time you would insert to a new hash map, and then the old one would just get erased.
Yeah, that
strategy was really nice. I like that.
That's okay. That's in the slides. I think that's actually in the slides. There's definitely a.
I definitely seen it though. Like,
okay, yeah,
I know
I
how
might
it
have not the better slides here, but there's it's all done, and then copy elements says, hey, I got them all, so I can toss it. Yeah. Okay. But concurrent hash
I
map
did
does a
think that
different
was one of
strategy,
the
but
fun,
never mind.
least recently used approximate strategies of I've got
Yeah.
a backing pool, and every time I touch something in the back pool, I move it to the front pool.
Yeah.
And then when I get to a certain size, I move the front to the back, and anything that was in the back is gone.
Right, in the prior back.
It's kind of a nice approximate least recently used.
Yes, because a standard least recently used actually requires atomic updates every touch. And Intel caching hardware, all hardware caches that want to have LRU like strategies don't do true LRU because it's too expensive, even in hardware. They do an approximate strategy. Yeah.
I just realized that if you had a thread, you check some data out, and then you sleep forever.
Yeah.
I don't know how I would be able to use that strategy, because I guess I would just see that it's still in use, and then
still in use. Yeah.
Put the pointer to the other table, but then all the entries have to be pointers, which is fine. Yeah, no, okay, yeah, that would work. Yeah, actually.
Right, it should work. But I guess the high level picture we get here is that concurrent hash map lifetime management has to have a different strategy than a single threaded lifetime management. And maybe that just requires different hash map codes, and you would just declare a different code. This is a hash map that is, lifetime is surrounded by the container, and he doesn't own his data. And there's a concurrent hash map where the lifetime rules are different.
Yeah. So that's the gist of how I would try to implement this. You get the one hash map that's for your nodes, owns nothing, and then the concurrent one that's much slower, but works across threads.
It doesn't have to be much slower.
Atomic
the concurrent
write?
one, by the way, the non-blocking hash map, it's as fast as a single-threaded good hash map implementation. Good generic hash map implementation.
Like every time you check out data, you have to write though.
No, if you're doing lifetime management, the lifetime management costs to say, I'm going to bump the ref count when I pull a piece of data out. That adds a cost.
Yeah, that's what I mean. That's what's going to make it.
But it's not going to be hugely slower, because the actual cost of computing a hash and doing a probe and lookup in the table is a bunch of work, whereas a non-atomic increment is like a clock cycle. So if you can
Well, it would
avoid,
have to be atomic because I'm telling the other thread that I'm taking the
Yeah.
data out.
if the data is already known to be shared globally, then you want to, on a checkout, not do an atomic update because that atomic update happened already.
You know what? One of the strategies I used is instead of using a variable to say if something's checked out, I put it into a queue, and the queue is only writable by that one thread. So the hash map would just check the queues of it would be a hardware thread, not a green. Like it would be on a per hardware thread, not a per green thread. But you would just insert it into the hardware queue, and then the hash map would just go through everything saying, I want to delete this. Is anyone using it? And then just read through all the thing. I think that would probably be more efficient, but
So I have
I got
my
to
20 core desktop. You're saying when I check something out or check something in, I touch 20 cores, hardware
Yes.
queues,
Yes.
and to see if
That because the alternative is the 20 cores are going to be touching the one spot. So it's either I visit all 20 or all 20 are banging on the one memory address to say they're checking it out.
Yeah, the 20 only bang on the one when, okay, so this is what Mark Falco's hack, and Ken said he did something similar here, was that the ref count picked up a bit saying some unknown thread atomically owns. So the first guy who checks out atomically updates the ref count to say an unknown thread owns. Now everyone who looks says, oh, some other unknown thread owns. I'm not going to touch the ref count. I'm not going to globally delete. And then they had some strategy that I don't remember where, when the guy who set the bit clears it or backs off, he went to another structure to say, oh, it's no longer atomically owned. He had a way to say, when I check out, I don't need to add anything to it atomically, but we couldn't get rid of it unless everyone, maybe you're all 20 guys, all have to go vote that they don't own. I don't know. All right, there's a thing to talk here, but I want to do it next week.
Yeah, no, I think I know how I would do that. That's actually pretty clever because you could just say the first person could just mark it as I'm using this, and then if I need to delete something and I see that bit set, then I visit all 20 cores or 160
Right.
threads.
You're exploiting the fact that it's highly asymmetric.
Yes.
Even the vast majority of shared pointers are never owned by two threads at the same time.
Yeah.
So if you sit there and say, here's my thing, it's an atomic reference counted, relatively expensive way to manage this thing, but nobody other than thread 6 has ever touched it.
Right.
If you are thread 6, you own it and you can treat it like a thread local. Now, if anyone other than thread 6 ever touches it, it sets that bit, and now you're out of cheap world and into expensive world where you need to go actually do atomic reference counting. But the fact of the matter is, most of the time, that doesn't ever happen, so you're fine.
Actually,
Oh,
yeah, that might be the
excellent.
good answer. You had two reference count pieces. One's the atomic thread and one's the my thread local. And the thread local guy is always cheap, but the atomic guy, you grabbed it. If you still own it, you're done. If multiples get on it, somehow it goes from thread 6 to either mini threads or a linked list or whatever, or some way to say there's a bunch of folks and now we have to be atomic.
You know, I really like that strategy. Like, yeah, you guys knew it. Yeah.
All right, I'm going to claim I need to have a bio break and it's lunch and I have things to do today. I get a haircut finally.
Cliff,
Way too much hair. I see way down the side of my neck here. It's down to here or something. Yeah, time.
do you completely understand how it would be implementing lifetimes, or are there still more questions that I have to ask you for later? Another day.
This is like, there's a theory on how it does it, and then there's an implementation where you find all the places where the theory is wrong.
Yeah,
But
yeah.
theory,
So that's what,
practice is great. In practice, theory sucks, right?
yeah, that's why like I couldn't answer your question because you wanted working implementation, and that's going to take a lot more lines of code.
Well, you take your pick, whatever. But at some point, I would love to see a working implementation, and then we can poke at it from a theory point of view and say, all these instances suck and all these work great or whatever. There's something to be done here. But
Yeah,
while it's sort of nebulous, hey, we can kind of sort of do, kind of sort of.
So
A lot of,
sounds like I have more questions to answer.
yeah.
That was
Yeah.
one
There's
of
a
my
lot of
favorite
reality getting
lines from
swept
my
under the rug
chemistry
that actually
professor.
needs
When
to
I
come
took
out.
Gen Chem, there was a lecture component and a lab component. And someone asked, like, why does this class require you to take chem lecture and chem lab in the same semester?
Yeah.
And the professor's response was, in theory and practice are the same, but in practice they're different.
Yep. Yeah, like that's
Yeah.
the right quote. All right. Any last minute comments, or I'm gonna bail? I'm gonna claim done. 3, 2, 1, done. All right. Good conversation. We can continue on Discord if you want, or we can go to next week.
Yeah. See you guys.
All right. Bye-bye.
Yeah.